Let's start with a puzzle, one that feels, well, impossible. It's something that will challenge pretty much everything you think you know about electricity. It's one of those things we use every single day, but almost nobody knows how it really works. So, let's figure this out together.
Okay, so let's dive into this thought experiment. We've got a simple circuit, a power source, a switch, and a light bulb just 1 meter away from the switch. The catch? The wires connecting them are ridiculously long. They loop halfway to the moon and back. So, you're standing there. You flip the switch. How long does it take for that bulb to light up? A second? 2 seconds? Or is it almost no time at all?
To even begin to answer that, we have to go back to the story most of us learned in school. You know the one I'm talking about. We kind of picture wires like a garden hose that's already full of water. The power station is the tap, and when it turns on, it pushes the water, or in this case, the electrons, all the way down the line to deliver energy to our homes.
It's a great story, right? It's easy to visualize. It feels intuitive. The only problem is, it's fundamentally wrong. The energy isn't where we think it is at all.
And this is where that simple story really starts to break down once you start asking just a few simple questions.
First off, in our AC power grid, the electrons themselves barely move. They just kind of wiggle back and forth in the wire. They never actually make the journey from the power plant. So if the electrons aren't coming to your house, what is?
Then you've got transformers. There's a literal physical break in the wire. Electrons can't jump that gap. So how in the world does energy possibly flow from one side to the other? It feels like it shouldn't even work.
And maybe the biggest mind-bender of all, since those electrons are wiggling back and forth, why isn't energy being sent back to the power station? Why is the flow of energy only a one-way street?
The answer, it turns out, isn't inside the wire at all. It's in the space around it. And this isn't some new age idea, it's a concept that completely changed physics way back in the 1800s.
It all started with the brilliant James Clerk Maxwell, who figured out that light was an electromagnetic wave. His work inspired one of his students, John Poynting, who came up with a totally radical new idea about how energy itself moves through space.
Poynting gave us what's now called the Poynting Vector. The easiest way to think about it is like a map or a rule for tracking energy. It basically says that wherever you have an electric field and a magnetic field crossing paths, boom, energy flows. And it flows in a third direction, at a right angle to both of them.
So let's apply this. When we flip a switch, the battery or power source instantly creates an electric field in the space around the wires. That field then causes the electrons inside the wire to start drifting, and that movement creates a magnetic field that circles the wire. Now we have both fields, an electric and a magnetic one, together. And here is the big reveal. The energy leaves the battery, travels through these electromagnetic fields in the open space, and then converges right on the light bulb. The wire doesn't carry the energy, it just acts as a guide rail, like a track for these fields to follow.
So if you remember only one thing from this explainer, remember that. Now, armed with this incredible new understanding, let's go back to our impossible puzzle.
The energy now has a choice. It has two potential paths to get from the switch to the bulb. It could follow the path guided by those incredibly long wires, or it could take the much shorter path directly through space.
Path 1 means following the guide rails of the wire for a journey of 600 million meters.
Or there's path 2. Just propagate across the direct 1 meter gap between the switch and the bulb. So what happens? Well, here's the crucial point. Electricity doesn't wait politely in line. The energy-carrying field bursts out into space and takes the fastest path possible. It takes the shortcut.
So how long does it take? The light turns on in about 3 billionths of a second. That's basically instant. The energy field crosses that 1 meter gap at nearly the speed of light. The answer to our puzzle was simply the distance, 1 meter, divided by c, the speed of light. Now, this might all seem like just a fun academic puzzle, but this invisible principle has had massive real-world consequences. This isn't just theory, this stuff matters.
People actually learned this the hard way. The very first transatlantic telegraph cable, laid back in 1858, failed after just a month. And why? Because the iron sheath they wrapped it in, which was supposed to protect the cable, was actually interfering with the electromagnetic fields and messing up the signal.
So this is the key takeaway. It's the invisible fields, not the physical electrons, that do all the heavy lifting. The wire is just the track for an invisible train of energy. This is the very reason we suspend power lines so high up in the air, to give those fields a nice, clear path to travel.
It's really amazing when you think about it.
Every time you flip a switch, you're commanding these invisible fields that fill the space all around you, delivering energy almost instantly.
It just shows that the world works in deeper, stranger ways than we're often taught. And it really makes you wonder, what other kinds of everyday magic, what other invisible processes are powering our lives just waiting for us to understand them?